Okie dokie. I will get started. So, last week we wrapped up with data structures, some sort of boring background stuff that goes on in R. Depending on which homework you did, you either played around with basic structures like vectors, matrices, lists, and data frames, or you got to do regression manually and had a whole bunch of fun learning how to manipulate matrices and extract sort of data from manually done math. Either way, you probably learned a lot more about just using objects in R and how things actually sort of work behind the scenes. Today we're going to jump back into the higher level, more applied stuff in R. We're going to talk today about getting data into R, getting data back out of R, and if you have data in R, how to clean it so that you can use it to do other things. So up until this point, I've mostly been providing what are pretty clean data sets, things that are already formatted nicely. We haven't had to do much with reshaping data in any way. At most, we've maybe created some variables or something like that. Maybe we've joined some data, other pieces of data. We haven't worked with data that come in what you might call natural format. Most data you encounter in the real world comes to you as a giant pile of crap. This is going to deal with that today. So, today's theme is data custodian work. That is, we're going to get it into R, we're going to clean it up, we're going to make it so it's usable for the things that people usually want to use R for. Okay, to talk about that, we're going to look at working directories and managing projects in R, importing and exporting data using Reader and Haven, which are tidyverse packages for importing and exporting data. There are base R versions of them, but Reader and Haven tend to work similarly or better in pretty much all cases with a couple little tricks. We're also going to talk about cleaning and reshaping data using the tidier package. The tidier package is one way of moving data from long format to wide format and wide format to long format. If you don't know what wide and long data are, you're going to learn about wide and long data today. We're also going to talk about working with dates and times using the LubriDate package. So date-time data is different from other forms of data because it's in sort of a different base. We're usually working with 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. You can't treat it like a normal numeric variable because you want it to roll over at 60 or roll over at 24 or roll over at 365. It's a different type of numeric variable. There's entire packages, entire systems for dealing with dates and times. We're going to talk about LubriDate, the tidyverse version of that today. We're also going to talk about controlling factor variables using the forcats package. Factors are tricky in R, so there's an entire tidyverse package dedicated just to handling factors, so you don't have to use clunky base R ways of handling factors. Okay, so a tour of a lot of different things at once, but it's all sort of vital skills for general data manipulation and handling in R. Okay, first thing, I want to review directories a little bit. Okay, you might remember that R looks for things like files that you want to open, files you want to save. It does all that in something called your working directory, right? If you want to find out what your current working directory is, getWD will print out what that is in your console, or actually it writes it as a string if you want to save it to an object or something. When I created these slides, when I ran these slides, the working directory for this happened to be here, my C drive, my OneDrive, GitHub, CSSS, my lectures, all the way down into week 5. This is what it was when I ran it. I did not have to set this working directory. It's because this folder, week 5, is where the file for these slides resides on my computer. Markdown documents automatically set whatever directory they are currently in to their working directory. Which means if you work with Markdown documents, often you should just, in fact, pretty much always, you should never set your working directory at all. Let it handle it by itself, and I'll talk about why in a second. Okay, if you do want to change your working directory for some reason, I will say you should resist this impulse whenever possible, but if you do, you can use setwd and give it some directory path in your computer and change it to that directory path. My suggestions for working directories, however, are use RMD files and just have the current directory operate as the working directory. Have everything saved within that folder or within some subfolder of that and never set the working directory. This makes it a lot easier. For larger projects, don't set a working directory, but instead use our Studio Projects functionality. Our Studio Projects, whenever you open a project on your computer, it automatically sets that as the working directory for every file you have loaded in there. I have some projects that have, 20, 30, 40 RMD and .r files in them. I want them all to have the same base working directory. I just use RStudio Projects. It handles all that for me. If I transfer my project to somebody else and they have that R project file in there, it will automatically set the working directory for them wherever they've moved that project to. I don't have to manually set any working directories, and if I share it with somebody else, they don't have to set anything either. That's ideal. A quick note, if you are a Windows user, if you copy a path from like the top of your Explorer window in Windows and you put it into R, you have to convert the backslashes to forward slashes for file paths, because Windows is stupid and bad and still uses backslashes instead of forward slashes for file paths. It's basically the only remaining system that uses backslashes instead of forward slashes for directories, and that's kind of dumb. R works by default in sort of a pseudo Linux or Unix environment for the way it handles things, which is always going to be forward slashes. Mac OS is Unix under the hood, so it's all forward slashes. So Windows is the last holdout on this. Even all operating systems on all your phones are forward slash operating systems. Windows is the last one. Anyways, you'll have to fix that. Okay. If you do need to set a working directory in a script, well, one, you probably don't, and you're just not thinking hard enough. But if you want to anyway, put setwd at the very start of the file. That way, if somebody else gets that file, they will see it right at the start, and they can edit it so it works on their computer. Keep in mind, when you set a working directory, it's going to be a different directory on every single person's computer. So as soon as you have setwd in something, it means your file can't just be run on somebody else's computer immediately, which is not good. But if you have to, now you know how. Questions about working directories? Should have messed with this a little bit. Okay. Projects in RStudio are a much better way to deal with working directories, especially if you have lots of files that are all kind of working from the same data, the same documents, things like that. Basically, in the top right in RStudio, there's a little projects drop-down you can use to create projects, open projects, things like that. This has a lot of advantages. One thing it does is it sets the working directory to the project directory for every single file you open in the project. It will remember all objects in your workspace, your command history, all that next time you open a project. And by all objects in your workspace, I mean, yes, everything in the global environment. Oh.
Yeah, I tried to do that, and I rearranged my folder, not in R, but in total, and it made a duplicate of it. So it insists that it must be there. It doesn't like want to shift to the one that I shifted.
Show that to me when you get a chance, and I'll diagnose it.
Yeah.
Okay. It will remember your objects in your workspace and command history, and this includes every file you have open. So very commonly when I'm working on something like, for instance, the slides for this class, I'll have the slides open as one tab, but I'll also have the course web page open as a tab, sort of my background structural files for the web page, for the course, my other slides, because I'm stealing content from my other slides continually, things like that. I'll have maybe, 10 files open. If I close that project, open a different one, all the tabs from that one are going to be open. If I close that and go back to my class one, it's going to open back up those 10 tabs I had open automatically. They're completely separate instances. It saves everything. Makes it a lot easier to deal with really large, sprawling projects. Okay? This really reduces the risk of intermingling different work using the same variable names and stuff. If you're always using a project file when you're working with particular scripts, it means that if you go and work on some script for something unrelated, let's say you're working on some homework assignment, you set a bunch of variables in it, but you want to go work on maybe one of your own papers you're working on, if you're swapping between different R projects, it wipes the global environment when you do that. You move between them, it doesn't save any files over. This means that if you have some variables that have the same name between two different projects, that's fine. If you just swap between the files in your tab browser at the top, anything in the global environment is going to take effect in all of those scripts you have open, which contaminates things. So I separate everything out. This class is a .r project file for me. Each one of my journal articles is a .r project file. Every presentation that I do for workshops and stuff is its own .r project file. I can swap between them. Nothing contaminates anything else. And it means that they're forced to all be in different folders on my computer like they should be. Okay. It's also easy to integrate with version control systems. For people who are familiar with Git, for version control, your R projects will just integrate as a single, like a Git file. It'll treat the R project as a repository. You can automatically have it update and push all your stuff to GitHub to mirror everything. Every single thing I do, every journal article, every lecture, every class that I teach, everything has its own GitHub repository. This class is being taught off of my GitHub repository for this class. Integrating Git into your stuff is really nice. It backs up everything, and you can see every change that has ever been made in this class. If you go look on the GitHub repository for this class, you can see all 370 edits I've ever made to any lecture slides in the class, and you can go back and see every edit I've ever done from the original time I generated the first set of slides for this class. That's kind of cool. Version control is really nice. It also means if I fucked something up here like a month ago, I could go back and undo it by looking through all the changes I ever made for the class. Basic software engineering type thing. We don't usually think about it as social scientists, but we should. Don't talk about it in this class too much, but if you're interested, let me know. Okay. Yeah, every RStudio project is its own GitHub repo. If you're interested in it, learn a little bit more, there is a link here. You can go. I have a presentation on reproducible research with RR tools that talks a little bit about version control. I'm not going to cover it here, though. Okay. Relative paths. So if you've set a working directory, or you're in an RStudio project and you have some particular working directory set, you can refer to any folders or files inside of that working directory using what are called relative paths. For instance, if I generated some plot in ggplot and I save it here, notice I'm not saying like c:/user/cclan my directory. Instead of just saying I want to save it to graphics/carsplot.png. What this is going to do is in whatever directory I'm currently in as a working directory, it's going to open the graphics folder and save carsplot inside that folder. This is called a relative directory path because it's relative to whatever the current working directory is. Relative paths are really nice because it means the locations of all loaded and saved files can be changed by altering the working directory. And they also allow others to download, say, your R script file or your entire project, put it anywhere on their computer they want, and everything will run perfectly fine. If I want to copy and paste all of my stuff from, let's say, I want to move everything off of my crappy OneDrive, because OneDrive is the bane of my existence, and move it into a Dropbox, I could just copy-paste this entire class into my Dropbox. Everything would work perfectly, because all my working directories are relative. If you have a whole bunch of files and every single one of them is like c:/, every one of those files has to be changed if you move it to a different location. That sucks. Use relative directory paths whenever possible. Does this make sense what this is doing? Any questions about this? Okay. Go bits. Okay. This is important for importing and exporting data because normally what you'll do is you'll copy all of the data files you want to import into R into like a data directory in whatever you use as a given project or homeworks working directory, and then you can use relative paths to access it. Okay, so a very first thing, if you're working with some what I call a popular data source, big surveys that are done all the time, census data, something like that, try Googling and seeing if there is some R package devoted to loading those data or downloading those data into R. Sometimes you'll find them on CRAN, which is the central R archive network, where if you hit install.packages, it automatically downloads packages from. Sometimes it'll be on somebody's GitHub. You can install GitHub packages by using DevTools. You may have to install this package. Install GitHub, their username and the repository. It will download R packages from that. I package my journal articles as R packages like this, so if people want to reproduce my research, they type in cclan/whatever the project is, and it can download my journal articles to their computer. They can reproduce all my code and see how ugly all of my code actually looks. But if you want to work with some data source that has an existing R package, it's a lot better to do that than to go and manually download it from their website. So some packages you'll commonly, or you might find are easy to use for R are things like World Development Indicators from the World Bank has a package called WDI. WHO accesses the World Health Organization API to download data. Tidy Census downloads data from the census and American Community Surveys and formats them in sort of a tidyverse format. We're going to use that in week 9 or 10 to download census data. Tidy Census also grabs geospatial shape files. So if you want to plot anything using census tracts, county or state boundaries, I actually use tidy census to download all those boundaries because they pop out in a nice data frame usable with anything else. That's how I get most of my shapefiles. QuantMod also here grabs financial data from a variety of sources. So there's often packages like this out there. There's thousands of them, and sometimes some organizations produce their own R packages for you to download data. The U.S. Census Bureau has its own R package for downloading data. Tidy Census actually interfaces, I think, in the background through part of that package. Yeah, there's lots out there. Normally, though, we're not downloading or using data from some source like that that has its own nice R package or maybe doesn't have a nice convenient API. Instead, they typically come to us as some sort of text format, usually what is called a delimited text file. Delimited text files are just, there's entries of data, and all of the entries of data are separated by either commas or line breaks at the end. The most common delimited file people tend to encounter is .csv, which stands for comma-separated value data. Comma-separated values look like this. You'll have some value like this, this. They're all separated by commas. Each observation is its own row in the data. This is CSV files. Sometimes you'll open up a file and instead there will be spaces. That's space-delimited files. Sometimes you'll see tabs, and they'll be tab separated or tab delimited values. Nice thing with all of those text data formats is you can figure out what the delimiter is, that is, what is the separator between data, by just opening it in a good text editor. When I say a good text editor, I do not mean Notepad on Windows. I mean literally anything that is not Notepad will be able to open large files. Notepad crashes on files that are over a couple megabytes. Anyway. Okay. Reader is an R package in the tidyverse that has a bunch of functions for importing data stored in text files. There's functions like read_CSV, read_TSV, read_delim does any delimited file. These are equivalent to the base R functions of read.table, read.csv, but they have better defaults, they are faster, and they generally sort of work better. I recommend using these whenever possible. They're really fast. One thing they do that's really nice is they do not automatically convert character data into factors. That's something some people should have seen on the homework, is that if you load something, say, with a data frame, you add some variables with a data frame function, put them together, character data gets converted to factors. Factors are annoying. We're going to talk about them later in this lecture today. Factors are complex, they're weird, they behave unexpectedly. Most of the time we want character data and we want to choose manually to create it as a factor later. All of these underscore functions by default just read it as character data and you have to specify them as factors later. Read.table, read.csv will load them all in as factors because what they're actually doing is reading the data and then running it through the data.frame function, which makes factors. These functions, read_CSV, TSV, and whatnot, are smarter about dates and times. They're not brilliant, but they do a pretty good job. Usually if you load in something that looks like a date time, like it'll be something like 10-30-2018, it will immediately recognize that as a date and convert it to a date time object so you don't have to do it manually. That's pretty neat. If something loads wrong in these functions and it produces errors, they have a function you can run, just problems, like after you've loaded the data, just type problems and run it. It will diagnose issues with loading your data in. That's pretty cool. And for really big files, it has loading bars. So you actually know R hasn't crashed, it's just loading a 2 gigabyte CSV file. Loading bars are nice. The default functions don't have loading bars, instead your system just hangs and you stare at it, wondering if it's broken or if it's actually loading stuff. I like loading bars. Reader is part of the tidyverse. If you've done install.packages tidyverse, it's already there. If not, you can do install.packages reader and get it. Library reader will load it. Okay. Importing data is pretty straightforward. So this example here, I'm importing some data on song ranks from the Billboard Hot 100 in the year 2000. If you want the whole URL for it, you could scroll over here. You could get like this. This is just coming off of Hadley Wickham's tidier repository on GitHub. What I'm doing here is I'm just saying I want to assign to an object Billboard 2000 raw the output from read_CSV. You'll see something that's interesting here is I'm not reading off my computer at all. You can give read_CSV the web location of a CSV file, it's perfectly happy to go send a request, download that file, and load it into an R object. It can take URLs, it can take anything. For most of this lecture, I'll actually be just downloading files off of either Hadley Wickham's GitHub repo or my GitHub repo. Okay, so it loads it in. When it loads it in, Reader spits out a whole bunch of output telling you what it decided to automatically do with these data based on what it looks like to Reader. So it says it has parsed these columns with these specifications. So it has read in the different columns of data in these particular ways. So whatever .default is, it came in as an integer. Artist came in as character, track came in as character, time, see, came in as call time with a particular format. It saw time data and it automatically converted into a date time object. The base data loading functions wouldn't know to do that. Weeks came in as character, 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 character on all of these. Okay? If you want full column specifications, so you can see, so there's actually there's a lot of columns. This is actually 66 through 76, but these numbers start at 1. So there's 76 columns worth of week data. Anyway, if you type in spec, you could get full column specifications for the whole thing. Okay, so let's see what the data types look like for the last few columns in this data set. So if I go structure, Billboard 2000 raw, and I'm selecting just columns 65 through number of columns, what does n call Billboard 2000 raw do here? Anyone have an idea? Yeah. Why would I want to do 65 colon number of columns? Yeah, I'm going from the 65th column of data set to whatever is the last column in the data set. Right? Number of columns is going to be whatever that number is. I think it's column, what is it? It starts at 65 here to 76, so it's like, I can't do math, so there's a lot of columns there. But yeah, okay. N-call is a good way to get the index of sort of the last observation, the last column in a data set. Anyway, so it loaded in these data. We see here that week 60, week 61, 62, all the way through 65 loaded in as integer data. Well, suddenly, a column that should be exactly the same as the previous week ones loads in as character data. So these week columns, which I haven't said yet, are what is that song's current rank on the Billboard 2000? Well, suddenly down here, a bunch of these started loading as character instead of integer. This is a hint that something probably went wrong behind the scenes, because these should all be integer. It should be, something could be a number 1 song. If it's the top 100, it could be only as low as number 100. I think this is Billboard top 100. So this should be an integer between 1 and 100. It should never be character data. Okay, what has gone on here is that the reader package, in the interests of speed, only reads the first 1,000 rows of data and looks for values in every column, and it uses those values to assign some data type to each column in the data set. The thing is there are very few songs in the Billboard Top 100 that stayed on the Billboard Top 100 for over 60 weeks. That's pretty uncommon to be a Top 100 song for well over a year, right? What happened was that in that first 1,000 rows of data, nothing charted for over 66 weeks in a row. So readers like, all I've seen is NAs for this entire thing. I don't want to accidentally lose any data, so I set it as character. Because remember, any type of data can be stored as character. You can put anything in there. Integer would be very limiting. It doesn't make any assumption it's going to be integer data. It just says, well, if I don't know what it is, I'm going to make it character. You can fix it later if you want. Okay. So basically, it assumed week 66 through 76 were character, so make sure nothing to be lost. If you want to fix that in Reader and you load in some kind of crappy data that look like these crappy data, you can manually set your column types. This is an example of one way to do it. What I did is I said, okay, I know that my first column should be an integer. My next 3 columns should be character data, and I know this because I've looked at what those columns are in the spreadsheet. This column should be a date. Then the next 76 columns should be integer. Rep I76 just generates 76 i's in a row. I paste it onto this, and then something that looks like this result, BB types here, is just going to be the letters I, C, 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 D and then 76 I's after it. If you look at the first letter of any data type in R, like integer is a lowercase I, date is a capital D, character is a lowercase c. What you're actually giving reader in call types is the first letter of a given data type in R to tell it how to read columns in. This is how you manually tell reader what type of columns you want different things to be. 98% of the time, none of you will have to do this, but when you do, if you don't know how to do it, you'll pull your hair out and scream. So this is how you do it. Remember, if your data are loading in weird as unusual data types, you can set them manually, steal my code to do it. Okay. So, an alternate solution to this, if you don't want to manually specify column types, is you can tell reader to look at more rows before deciding what a given column is in a type of data. You could say read underscore CSV and then set guess max 5,000. By default, reader looks at the first 1,000 rows of data. This would make it look at the first 5,000 rows of data. You might be like, wow, that's a lot of rows. But if you routinely work with files that have millions of rows and a lot of NAs, you probably don't want to just be like guess max equals 10 million, because it's going to take the time to read the first 10 million rows. And unless you really want to go get coffee or lunch while you're waiting for it to read your data, you should probably just specify the column types manually. Okay. Another thing you could do is you could use read.csv in the foreign package. That's a base R alternative. It is much slower than read underscore CSV, and it's a bit dumber. What it does is it actually does just read every single row in the data set. So it could never ever be faster than read underscore CSV. At best it will be the same speed, but if you don't like typing in things like that, go ahead and use it. It will also make all of your character data into factors. Okay. And this is how to make it not do that. I recommend using reader pretty much all the time. Okay. So, Excel files are something we commonly deal with. We get a lot of spreadsheets as Excel files. The easiest way to open an Excel file in R is to instead save it as a CSV file and open it as a CSV file. Normally I would just say export your Excel data as a CSV. Sometimes, however, you're working with Excel files that are sort of files in motion. They're continually being updated or edited, and so you just want to draw directly from the Excel file. You never want to open Excel and convert some file or something like that. For that, I recommend one of these two packages, either readXL or OpenXLSX. I think they're largely equivalent. I don't really use either of them because I just manually save my stuff as CSVs. I hate receiving Excel files. If you work with Google Docs spreadsheets, there is a Google Sheets package. Google Sheets package makes it so you don't have to download your spreadsheets at all from Google. You give it your Google account information and it can query documents that you have access to through your Google account and just download them directly. This is really good if you're working with Google Sheets that are updated a lot. Let's say you have live data collection going, maybe you have people in the field who are filling out a survey, or you've got some kind of thing running through Google Analytics that goes to your sheets. You can just automatically have it download through that all the time. I like things that are automated and require me to put no effort into doing them. That eliminates the manual thing where I have to save a Google Sheet and open it. It's pretty nice. So, with any of these things, like loading Excel files, Google Sheets, or anything like that, you will not keep any text formatting, color, comments, or merged cells in your data. So, you'll have to get creative if you want to actually store that sort of information. The thing I will say now is if you were storing anything of importance, like actual that has a real meaning, like it indicates something in your data, in the text formatting, the color, the comments, or the merging of your cells, you should stop doing that and never do it again. That is what is called metadata. Useful information is not meant to be stored as metadata because metadata is unique to applications. Anything like text formatting, color, comments, anything in Excel, that is something that is only in some Excel particular format in that thing. It will never be read correctly by anything other than Excel with any reliability. Saving things as metadata is a major no-no in the world of like analytics, data, software engineering. It should be in life. Don't do that. Okay. So, rant over. Okay. Often you want to get data out of R and you want to hand it to someone else. Well, most other software packages can read CSVs. Excel can read CSVs. Very often we just want to write the data out as a CSV. I use CSVs also as a long-term data storage format. CSV files are ancient beyond time. They are just slightly newer than fixed format punch card data. Things on magnetic tapes are sometimes on as comma separated values. It's old, everything can read it, right? If you can open it, you can open raw text, ASCII text, one of the oldest computer formats in existence. You can read a CSV file. It's good for storing stuff. Anyway, if you want to save them, generate those things, write underscore CSV will write whatever R object you give here to a given path. So in this case, I say Billboard Data CSV. That will write a data file, a CSV file, with all the Billboard data in it to my disk. Okay, so sometimes you don't want to save as a CSV, maybe because it's a really big file, maybe because you want to load fast, maybe because you know you're only going to be working in R. So, or, big one, maybe you want to store R's metadata. Like I said, metadata is something that is lost when you open it in another application, but metadata are very useful within a given application. Metadata in R is stuff like what type of data is a column. Something being character data is metadata for R. If I write it as a CSV and hand it off to somebody in Excel, it doesn't say that's character data. Excel has to interpret it. But within R, it's useful to know whether something is a character, a factor, numeric integer, whatever. That's metadata in R. To preserve that, I need to save my files as a .rdata or .rds file. Okay? If you want to save a .rds file, well, a .rds file is used for saving a single R object, and it doesn't save that object's name. I very rarely use this, but sometimes people want to do it. You do write RDS, whatever was the object's name, and then some path to write it to. To load it into R, you need to have a new object name and assign that particular thing from it. Normally, I would save R files as .rdata or RDA. This can save some arbitrary number of objects into a single file. You could give it 10,000 objects, and it will load into your environment all 10,000 of those objects with their original names, if you want. Okay? This is just the save and load commands to do this. Okay? Notice there's no assignment operator here. It's because these objects have their original names, and when you load them, they go into your global environment. Okay? I pretty much always save things as .rdata. There's one other reason to save things as rdata or RDS files over saving them as a CSV. RData files are binary files in our sort of native language. They are between 1/10 and 1/100th the size of a CSV file, and they load 10 to 100 times faster than a CSV file. If you have really large data sets, save them as RData files. It will compress them and load them much faster than a CSV. But keep in mind, anyone who does not use R can't open those files. So it's a trade-off. Always have a CSV backup of everything. Okay, so the dput function. I think I mentioned this maybe briefly in the first week. When you're asking for help, say on the Slack channel, over email, Stack Overflow, Stack Exchange, something like that, it's useful to prepare a snippet of data for people to use so that they can actually troubleshoot your problem. If you say like, oh, here's all these functions I ran on something, I'm getting this error, they'll be like, that's real nice, but unless you give me some reproducible piece of data to run the same functions, I can't help you. Dput is for doing that. If you do something like dput head cars 8, the output is going to look like this. It's going to say structure, list, speed. These are all the values of the speed variable, all the values of the disk variable, the row names, the class of the object. This is essentially you dumped the head of the car's data as a reproducible, reusable, transportable object. If you copy-paste the output of dput directly into your R console and assign it to something, it will regenerate this original output as an R object. This is essentially how you could email an R object to somebody. It's pretty easy. If you want to ask for help on like Stack Overflow, dput and just paste this output at the top for the object you're working with. In this case, this is only the first 8 rows, but that's probably enough to troubleshoot something that's going wrong. Okay? Same thing for emailing me, emailing the list. Use this method. Okay. Very often, we are working with Stata or SPSS users. Very often, we are the Stata or SPSS users, and we want to bring in data we've been using in those software packages into R. There are two common ways to do this in R. There are two common packages, rather. There is Haven, which is a tidyverse package for loading in data. It handles data from things like Stata, SPSS, SAS, a few other packages. Then there's also the foreign package, which is a base R package. It's built into R that works also for Stata SPSS. It does Minitab. It has a primitive SAS routine. For less common formats that aren't in there, Google it. As I think I said before in the first week, I've yet to encounter some data format out there that doesn't have either some R package to handle it or some clever hack to make it work in R. They pretty much don't exist, and a big reason for that is that pretty much all software out there, most software out there, is actually outputting things as raw text, even if it doesn't look like it. It's really easy to process raw text. If you have some file, you know there's data in it. There's some kind of data in there, but it has some ambiguous file extension, like .dat, one of the most common file extensions in existence, is meaningless. Everything says something called .dat. Try and open it up in a good text editor. Again, by good text editor, I mean something like Atom, which is GitHub's text editor, Sublime, which is a commercial product, but it's pretty good anyway. Vim or Emacs, if you're one of those people. Good chance that anything that's a .dat is actually a delimited file or a fixed format file. Then, when you see it, if you see a bunch of commas, change its file name to .csv. Open it in R. Or don't even that, just do read.csv on it, on that file name, it should open it. If you do find something that you want to open and you do not know how to open it and can't find a solution, do please email me. I'll probably be able to figure out how to open it. The only semi-exception to this is I have some file on magnetic tape I've been trying to get off for a while, but the problem there is not that R can't read it, it's that there are none of the appropriate magnetic tape readers in the state of Washington, and I don't want to ship it to someone. That's a real problem. Hopefully that doesn't happen to you. Okay, so boilerplate stuff is over at the beginning of the lecture. Now we can actually work with data. Let's clean some data. Okay, so initial spot checks. When you load in a new data set into R, if it's coming from some natural source, and by natural source I mean something like administrative data, it's usually administrative data that ruins your life. When you load it in, there's some things you want to check, basically any new data loaded in. The first thing is, did the last rows and last columns from the original file make it in? Typically, the first rows and the first columns make it in okay, and it will be obvious if they don't. But the last rows and the last columns are often missed, especially in large files. Get the tail on things, look at the last columns, that sort of thing. If you have the last rows or columns coming in weird, you may have to use a different package to load the data, or you may need to manually specify the range of something. It might be just some strange thing going on. That's one of the most common problems. Next, check to see if the column names are in good shape. Good shape being like, are they sensible column names? Sometimes you'll look at the column names and you'll see numeric values. That might mean that that data set doesn't have any column names and it accidentally loaded in the first row of data as column names. Other times, the column names, like the very first column, will actually have an entire paragraph of words. That's because you opened up maybe a tab-separated file as a CSV. It had no separators, so it took the entire first row and made it just one column. If you load in a data set you're expecting to have like 20 columns and it has one, you're probably using the wrong delimiter. You probably loaded in a CSV as a TSV or a TSV as a CSV. If that confuses you, ask me questions. Okay. Column names can be fixed by specifying column names manually, renaming them with dplyr, that kind of thing. Okay, so are there decorative blank rows or columns to remove? This is the Excel problem. People use spreadsheets in Excel and they like to decorate them, do weird things, merge cells, color stuff, bold things, format it like it's a word processor, and other behavior that is not meant to go into a spreadsheet. So, very often there'll be something like 2 blank rows at the top of your Excel sheet. That sort of thing pisses off data analysts because they now have to tell their read function, ignore the first 2 rows. There is a skip argument in read_CSV that says skip this many rows at the beginning. You just have to do it manually and then browbeat whoever generated the file for including decorative rows. Okay. You can also also filter or select to remove them. I prefer to do it in the actual call to read_CSV, but you can just eliminate them that way. Okay. So, another thing to do when you're loading in, figure out how missing values are specified in the data. If they are blanks, sometimes they will come in appropriately as NA in R, which is nice. Sometimes, however, missing values are a space in the data. R will just read that in as character data. A space is a character, right? Sometimes you'll load something like something that came out of, say, Stata and was converted to text and given to you. Stata displays a period as its missing value. Well, now you may have to replace every period in there selectively with an NA. Files coming from SPSS and some software very often use like 999 as a missing value or 9999 as a missing value. Well, the thing with that is that you could legitimately have columns that can have 999 as an actual value, so you need to sort that shit out. It might take some effort, it might take some like looking around. If you load survey data and use survey data, one of the things you should always do is read the code book to your survey. Code books and surveys will tell you what they're using as missing data. It's often negative values, or it's 999, 99999, whatever, right? Look at those things, convert them manually to NAs. So you could manually do this here with mutate and if else, but also in functions like read_CSV, you can also specify values that are always missing values, and upon loading it, it will convert those to NAs. Remember, NA is the only valid missing data type in R. Okay. Another thing that's common in data is sometimes character data of some kind will be loaded in incorrectly as numeric, or numeric data will be loaded in incorrectly as character data. One of the most common ones is R will see a bunch of zip codes that have, say, leading zeros on them, so it'll be like 0098115, my zip code, and it will be like, well, that's numeric data, those zeros contain no information, and hack all those zeros off. Maybe those zeros should be there for some reason. Maybe you're in one of the East Coast zip codes that actually begins with a 0, right? You want those in there. You can tell in call types in Reader, you can tell it to load those in as character data instead. ID numbers in a survey are always character data. They have no meaningful numeric value. Make them character data, or when they pop in, the data pop in, you can mutate and convert them to numeric or as character or whatever you want to do. Okay, so this is a list. Anytime I load in new data, I basically run down this list, and then in the back of my head, I run down through all of some of the horrible, unsuppressible memories of bad data files in the background that have similar problems to this. Over time, you'll remember your own checklist of things, that the horrors you've encountered in working with actual data. You'll know all those problems when you see them. Okay, so here's an example of slightly messy data. In these data, an observation is a group of students from a program at UW of a given gender. So for instance, there are 10 female Evans School students, there are 3 male public health students. The variables in this data set are the program and the gender. Well, notice that there's 2 columns here, but female and male is 1 variable, not 2 variables, right? Those things are mutually exclusive in this particular set of data, so the information is being conveyed in 2 columns when in reality it's actually 1 measure. So for instance, the values here, program, that's where that stuff should be. Evans School Arts and Sciences, Public Health, Other. Gender, female and male, is in the column headings. It's not its own column. And the count of individuals, which is 1 variable, doesn't even get its own column, right? Instead, the count is split over 2 different columns. Okay? This is what we call slightly messy data. It's not in a format useful for analytics, but this is the type of format you might provide to someone to make a nice crosstab that they can read. You wouldn't be able to plot this in ggplot or something, but, you know, it's only slightly messy. A tidy version of this, something ready to throw into ggplot or something like that, would look like this. Each variable is a column. So now we have program, gender, and count of people. So each concept captured in these data is its own column. Each observation is only a single row, instead of there being 2 observations per row that we had in the previous one. Something like this could go straight into ggplot. You could do something like make a plot where you grouped by Evan's school or something like that, color-coded things by male and female, something like that, and then the counts would be maybe your Y variable or something. This can go straight into ggplot. Okay, does that make sense, the difference between these? This is what's referred to as long data. This is what is referred to as wide data. Okay? We will dwell on this far too much today. Okay, the Billboard data I loaded in earlier is not kind of messy, it is hideous. It is terrible. The format is gibberish. Yeah, so what we have a column for the year. It's all the same because it's the Billboard Top 100 of 2000. We have the artist. It's a sensible column. We have the track. It's sensible. We have time, but time is in minutes, seconds. It's not numeric. This is actually character data that R has no idea how to interpret without being converted to something else. Date is fine. Date's a date column. Then we have 76 columns that all contain the same information. They are the position a given song was in that week since it entered the Billboard Top 100. Okay, I'm going to repeat that. That's a really weird format. The way these data work is that, for instance, this 98 Degrees song entered the Billboard on 8/19 year 2000 in 51st place on the top 100. 1 week later, it was at 39th. Another week later, it was 34th. The thing is, though, is that the week 1 position of any given song is not the same week 1 as any other song, because what week 1 is defined entirely by the date that it entered. So these things are not lined up in any way. It's all relative to some date that's kind of arbitrary. They're spread across the board. These are weird data that are not lined up in some way that makes sense to most people, and they have 76 columns of information here that should really all be contained in a single column. Okay, so the observations, again, are the week since entering the Billboard Hot 100 per song. The actual observations are weeks, right? The variables in the data are the year, the artist, the track, the song length, the date it entered the Hot 100, and the week since it first entered Hot 100, spread over 1 million columns, and that rank also spread over 1 million columns. Okay? The values in the data are things like the year, they're all 2000, bands, songs, the length of those songs, what week it is. So week 3, those are in column headings, but the rank is spread over lots of different columns. It's a weird format. To try and plot it in ggplot, it's going to have no idea how to work with any of that crap. Okay, so what tidy data are and what we're going to convert this thing into, they're also called long data. If you're in some statistics class and they talk about moving from wide to long data, tidy data are long data. Long data have all the values for a single observation in their own row. One observation per row. The values for a single variable are all in their own column. They're not spread across multiple columns. And the observations are all of the same nature. And by all the same nature, I mean they have the same type of unit. So if you have observations that are, say, person years, which is a common survey unit, every row is a person year. Might be for a different person or a different year, but they are all person years. You don't suddenly have a person month lodged in with the rest of them. That should be split into 12 different person, or that should be collapsed rather into one person year. Okay, so why would we want tidy data? Why are we so strict about the particular format of the data? One of the big ones is that it's a lot easier to understand data that has many, many rows and few columns than many, many columns and few rows. We are really good at looking at things vertically, but when things start expanding way out, it gets really awkward. And it's just honestly because of the way we're used to using technology and things like that, we're always working with long things, okay? It's also required for plotting in ggplot, so philosophical, purely technical. ggplot expects you to have long data. Many types of statistical procedures, hierarchical models, mixed effects models, that includes longitudinal panel models and things like that, all expect your data to be in long data format. Very few things expect your data to be in wide format, except the mlogit multinomial logit package, and all structural equation modeling software expects wide format. Take a class like that, you'll understand why. Another thing about long data is you have very few columns, so you have fewer confusing variable names. We do not have week 1 through week 76, we just have a week column. The numbers in it will tell you what week it is. Okay? There are also fewer issues with missing values and imbalanced repeated measures data. So if you put every single observation, so if I take all 76 of those weeks, collapse into one week column, if there is something that does not have an observation for week 76, it just doesn't need a row. It has no row, there's no observation there. If I have 76 week columns, if something wasn't observed in any week except the first week, it still has an NA in all 75 other columns, right? Wide data wastes a ton of space. Long data compresses things greatly. Okay, so the tidier package in R, part of the tidyverse, one of the core packages in there, provides functions for tidying up data, similar to if you're working Stata, the reshape functions in Stata, in SPSS, vares to cases. Key functions in tidier are gather. Gather takes a whole bunch of columns, 2 to thousands. It will take those columns that are wide data and it will rotate them down to make 2 columns, one that has a key, one that has a value, and we're going to talk about what keys and values are. So it takes any arbitrary number of columns. So I could take those 76 week columns. So if we originally had, we have week 1 all the way through week 76. What gather will do is it will take these 76 columns here, it will rotate them down. If I say rotate, I mean it's really wide. Imagine you took them all and made them really tall. So you now have a we have a key, which is the original column names. So, for instance, you'd have a key, we have a value. The key would be 1 through 76, and the value would be whatever numbers were already in those columns. So, for instance, this is a whole bunch of different song ranks for that week. This song's rank in week 1, this song's rank in week 2. Well, now instead you're going to go and have a whole bunch more observations, but each song is going to have, so in week 1 this was its value, in week 2 this was its value, in week 3 this was its value. Every single song will have 1 to 76 rows and a value associated with that. So we've taken a ton of columns, rotated it down like this. Does that make sense? We're going to play with this a bunch. Okay. So the key is whatever week it was numerically up here in the column name. The value is whatever was actually in the set, just as a clarification. Okay. Spread inverts that gather operation. So gather will take 2 or more columns and rotate them up into multiple columns. So in pretty much everything in the tidyverse and all sort of good software, any operation you can do, you should be able to undo in a straightforward fashion. Spread undoes whatever we want. Most people don't use spread very much. I do a lot of structural equation modeling, so I turn a lot of long data into wide data all the time. That's what you use spread for. Separate is a function that's a little different. Separate pulls apart one column and generates multiple columns. This is really common if you've gathered a bunch of data where values were embedded in the column names and you want to get out some sub-element of that. For instance, a common operation is, we'll use extract numeric, which is actually a type of separate here. If I had done this gather on the week data, this key isn't going to be 1, it's going to be week 1, week 2, because those were the column names, right? Well, if I run extract numeric on that, what it's going to do is it's going to be like, okay, nobody cares about all this text, let's just eliminate it down until I find numbers, and it would turn them into 1, 2, 3, 4, 5, 6, 7, 8, out through 76. That's a common thing we want to do if your data are like, you've got 100 columns that are named things like married 18, married 19, married 20, marriage status at different ages. Well, I probably only care about the numeric thing, the age. I would generate a new key called age, and I would extract numeric and get that number out instead of married 18, married 20, so on and so forth. We'll play with that a tiny bit. Okay. Another one, I have never actually used this myself, but I know it exists, is the unite. Unite will invert separate here by gluing together multiple columns into one character column. If I ever want to do this, I would probably just paste them together, but unite kind of does that operation. Okay, gather. Gather is the heart and soul of the tidier package, so we're going to play with it a little bit here. So what we want to do is we want to use gather to get the week and the rank variables out of their current layout and put them into two columns. In other words, we just want to do what I just was drawing on the board here. Okay? We want to get, as a result, a big increase in rows. A huge increase in rows. Because every single, like one of those variables, every one of these entries is going to be converted into a new row for that particular song. So a song that was actually on the Billboard all 76 weeks there is going to now have 76 rows. Okay? But there's going to be a commensurate giant drop in columns, because we're going to cut out 76 columns and replace them with 2 columns. Works like this. I load up dplyr, load up tidier, then I'm going to say the new Billboard 2000 data is equal to the old Billboard 2000 raw data. I'm going to gather. My key, the key is something I'm going to generate. It's a new variable. I give it a name. The key is week, so the new variable is going to be named week. The value is rank. The new value column is going to be named rank. And what am I going to gather? I say we're going to gather every column that starts with WK. Okay? This is a helper function, the same type of helper functions we found in select in dplyr. There are 76 columns that begin with week that contain all that week data. I do not want to type out all 76 column names. So I say, okay, help me out here, man. Let's look for things that start with WK. Just stick them all in there and gather them for me. Magically, it does it for me because it's smart. Now I gather these data to Billboard 2000. If I get the dimensions on Billboard 2000, look at that. Now it has 24,092 rows, and it only has 7 columns. We just squished this data set to be really, really vertical. It's always falling apart on me. Really, really vertical, really, really narrow. Okay? Another way I could do the same thing, by the way, instead of starts with week, is I could say week 1 colon week 76. Remember the colon operator creates like it runs down a range of things? Inside of gather and inside of select in dplyr, you can actually just use names and it will run down a list of names. Kind of cool. So if you have contiguous columns, you can say run through this whole range of. Okay. These are what the new data look like. If I get head on Billboard 2000, well, we still have year, we still have artist, we have the track, we have the time, we have the date entered, but now all of those week columns are now just 2 columns. We have the week, and we have that song's rank in that given week. I've only displayed week 1 results for all these songs. We can see these if I scroll back to the previous slide with that data. These are all the exact same songs in the same order with the same ranks in those given weeks, right? The thing is now is each one of these songs actually has an extra row for every week it was on the Billboard. If you expand this out, you'll be able to see that. Okay? This operation makes sense. Week, rank, any questions? So I keep poking at it here. Yes?
Sorry, that means for each song we have 74 rows.
76 rows, yeah.
76 rows.
Yeah. Every single song will have 76 rows at the moment. But remember, some of these songs were not on the chart in later weeks. We're going to take care of that in a second. Okay. So, if I do a summary on the rank for Billboard 2000, we will see that even though this is 24,092 observations, 92 rows, well, 18,785 of them have an NA for rank. The reason for that is we took all of those songs that were only on the chart for short periods of time and then still generated a row for every single one of them even when they were not on the chart. Well, if they weren't on the chart, we actually just don't care about them at that particular week. We don't need 76 rows for every single song. What we want is we want one row for every week it was actually on the Billboard, and we can get rid of all the rest of them, right? So, gather takes an na.rm argument the way many functions in R do. If I give na.rm to gather and otherwise run the exact same operation, any row that would have ended up with rank, that is the value here, as na, just gets dropped, because we actually don't care about those observations. They didn't have a rank there, so why keep them in the data? If I do that, now we see the NA thing that was on summary before, right there, NAs, well, there aren't any NAs anymore. It got rid of every single one of them. Now our data set has no missing data, because before the missing data wasn't actually informative. It's not true missing data, it just does not exist. Now, our ranks are from rank 1 to rank 100, rank 1 being the best rank on the top 100, and 100 being the lowest rank. All of our missings are gone. Does that make sense what that did? It shrunk our data a lot, too. We got rid of 18,785 rows. If we were in wide data, there would be no way to actually drop those, because those columns contain those NAs, but we can't get rid of parts of the column. They're all there. Long data is also more compact than wide data, which is interesting. Okay, so separate. So if we look at our tracked length column, our tracked length column is something that is not, as I say, analytically friendly. It is things like 3:22 to mean 3 minutes and 22 seconds. That is a good human digestible format. People know when they see something like that it means 3 minutes and 22 seconds. And people know what seconds are and what minutes are. That is not a digestible and useful format for a computer, however. So what we want to do is we want to separate our minutes and seconds into something else and create a new numeric column for the length of a song. So what I do here, I'm going to overwrite my Billboard 2000 data. I'm going to take Billboard 2000. I'm going to say separate. We're going to separate the time column, which contains data like 3:22. I'm going to separate into two new columns. The columns are going to be called minutes and seconds, and I want to separate the data at colons. Anywhere it encounters a colon, put the first thing into minutes and the second thing into seconds. Okay? Convert equals true tells it to convert those into numbers. Don't leave them as character data, convert them over to numbers. Then we're going to mutate and create a new variable called length. The length is going to be equal to minutes plus the number of seconds divided by 60. So what is length going to be in units of? Minutes. Minutes in decimal, right? So something that was 3 minutes and 30 seconds long is now going to be 3.5 minutes long. Humans aren't good at digesting decimal times, but it's more sensible for a computer. Okay? Then what I do is I drop the minutes and the seconds columns I created here because I just want the length. Now, if I do summary, Billboard 2000, and length, I can see that the shortest song here was 2.6 minutes long, and somebody had some Freebird shit out here at 7.833 minutes long. I now have numeric decimal times. Okay? And I could plot those nicely in ggplot. I could not plot 3:22 in ggplot. Okay? Does that make sense? Have you any questions about separating? It's a common type operation. A lot of data you'll get will be formatted like that. Break it apart, put it back how you want it. If I wanted to make the seconds instead, I could have just done minutes times 60 plus seconds would have been the same time in seconds. Okay. I'm actually curious what 7.8 minute song there was in the Billboard 2000 that would have stayed up there. Should look that up. Anyway, so parse number. Tidier has a convenience function to just grab numeric information from a column. Very commonly you'll have something like, for instance, week, which we only care about the actual numeric part of the week. We don't care about the word week sitting in front of all of them. So what I do here is I say, take our Billboard 2000 data, mutate, week equals parse number week. So I'm overwriting the week variable. All I'm doing is saying parse number week. That's going to delete all of the text in that particular variable, pull out any numbers and assign them there, and automatically convert it to a numeric variable. So now if I get summary on Billboard week, we can see week is now a numeric variable. You can tell because it's decimals. It starts at week 1, it ends at week 65. Okay? If you need to do something more sophisticated than extracting a single number from it, you're going to have to learn things about conversion or pattern checking in string parsing, which is week 8. String parsing is usually done through something called regular expressions, which is a logic of text. We're going to learn that in this class. It's very useful and powerful. Okay, so spread's the opposite of gather. You'll use spread if we have data where the same observation takes up multiple rows. One example you might see is you might end up with data that look like this. You might have something where you've got like a group, and then in this case I have a statistic. So I have, for group A, I have its mean, its median, its standard deviation, and for group B, its mean, its median, its standard deviation, and then some value for that. Okay? This would only really be useful if I wanted to say generate a ggplot where I wanted to say facet on the statistic and plot all of the values for a whole bunch of different groups. That's way safe if you want to provide summary statistics for, I don't know, genomic data and you've got 10,000 genes and you just want means, medians, SDs for all of those. You could do something like that in facet and do it. Most of the time, we think of the mean, median, SD as something that would be a column in a data set instead. This is an example of where we want to spread these to turn a pair of columns into multiple columns. Works like this. If I have data like this that are too long, we want them to be wide. So that was the same data I had before. I can say, take my too long data, spread them. The key is the statistic and the value is the value. It will automatically know what new columns to generate based on the values of statistic, and it will populate the cells sort of the table using the values. So if I look over here, statistic had all of these values, and then value had these values. Now the values of statistic have become the column names, and the values of value have become the actual cell values. The thing has been squished this way, made wider. That's how you'd spread. It's the opposite of gather. If we wanted to gather this back into this format, we would have to say gather, key equals statistic, value equals value, mean colon SD would get mean, median, and SD. So you could reverse that operation if you want. Make sense? It's okay if this one's a little weird, as long as gather makes sense. Okay, so let's keep chunking around here on the top 100 of the year 2000. So what I want to do is I want to look at songs that hit number 1 at some point and see what their trajectory through the top 100 looks like compared to all the songs that never hit number 1. So what we're going to do here is first I want to find the best rank that every song in the Billboard hit. Right? This is going to be a single number for each song. What do we normally do when what dplyr function would we use when we want a single number for something or some set of rows? Exactly! Summarize. Okay, you can tell because it's highlighted. Okay, so we're going to create a new data frame called best rank. From Billboard 2000, I'm going to group by the artist and the track. This is only really necessary to group by both artist and track if two artists have the same name track. I don't know if that's true in here, but maybe they do. We're going to summarize and say the minimum rank is equal to the min of the rank column. The minimum rank is going to be the best rank it hit because number 1 is the best rank you can possibly hit. 100 is the worst rank on here. So minimum is getting the best or the highest rank. Then I'm also going to summarize how many weeks was this song at number 1, and that's just equal to the sum of rank equals 1. Do they have a guess on why this works? What is rank equals 1 producing? Trues and falses, or 1s and 0s. Okay? Because trues are also a 1, and falses are also a 0, you can get the number of weeks it was at number 1 by getting a bunch of trues for every time a song was at number 1 and falses for when it wasn't, adding them all together, and that gives you the number of weeks it was at number 1. You're summing up a logical vector. Okay? Then I'm going to mutate a new variable called peak rank, which I'm putting a space in just because I'm feeling fancy. Then I say, if else, the minimum rank was 1, so the best rank it ever hit was 1, I'm going to assign it the value, it hit number 1. If it never hit number 1, this will be false, and it will assign it the value didn't hit number 1. Okay? Since a variable that only takes 2 values, its character, it looks like that. And then, so this is one entry for each song in the entire data set. But what I want to put it with is all of my original track data. The track data has many rows for each song, so I'm going to join them using the joins we learned in week 3. I'm going to say Billboard Data is now going to be equal to Billboard Data joined onto this best rank data frame by artist and track. So let's say some artist was on the chart for 10 weeks with one particular song. All 10 of those songs, all 10 rows in that data set, are just going to have repeated whether that song ever hit number 1 or didn't hit number 1. Okay? We'll see why this is useful here in a second. Okay, so now we're going to plot this. This probably looks intimidating. This is a lot of plotting code, but I'm going to walk through it and explain what we're doing so it makes sense what it looks like in a second. So I'm going to say I'm going to generate a plot called Billboard Trajectories. It is going to be ggplot with our Billboard 2000 data that has that new column we added to it through that merge. X is week, so we're going to be plotting on the x-axis along weeks of our data. Y is rank, so it's going to be a line of ranks over weeks. I'm grouping by track so that I can make the lines follow a single track and not just like a whole bunch of dots. I'm going to color it by peak rank. If you remember, peak rank only takes 2 values. Peak rank is either hit number 1 or did not hit number 1. So everything that ever hit number 1 is just going to be one particular color. Everything else is going to be a different color. So this will separate out the ones that ever hit number 1. I'm going to do a line plot, GM line, AES size equals peak rank. What this is going to mean is that the lines for things that ever hit number 1 are going to be bigger than the lines for things that did not hit number 1. The size is controlled by the value of peak rank, which only takes 2 values. Alpha 0.4 is going to make it so the lines are partially transparent. Okay? Making things partially transparent, great when you plot a lot of things that overlap. As we'll see, the lines overlap a lot. Next, I'm rescaling time. I said scale x log 10. The reason for that is that I want to highlight early weeks. Logs compress higher numbers. So basically what's going to happen is that a given unit of time will be this long at the beginning of the axis and like that long at the end of the axis. It's just compressing the later things. Logging things, play with it in plots. Sometimes it makes things look a lot nicer and easier to understand. I do scale Y reverse. So if you remember, the best rank in the Billboard Top 100 is 1 and the worst rank is 100. If I plotted it normally, songs that hit number 1 would be hitting number 1 down here and then climbing back up to worst. What this is doing is it's just flipping that up, so number 1 is at the top. Okay? Then, theme classic, makes it look a little less ugly. I give an X lab, a Y lab. Then I set some manual things. I say, scale color manual, the values are black and red. What this is going to make it is that whatever is being colored is going to take either the color black or the color red. Remember, what we're coloring by up here is peak rank. What this means is that things that did not hit number 1 are going to be black. Things that did hit number 1 are going to be red. And that's based on the factor levels of that particular variable. Scale size manual says 0.25 and 1. The first level for peak rank, and remember size is being set to peak rank, the first level is things that did not hit number 1. They're going to be 0.25, they're going to be tiny. Things that did hit number 1 are going to be real big. So far the lines for songs that hit number 1 are going to be red, and they're going to be big. Then I move my legend inside to clean up my plot, and this just says get rid of the hideous background. ggplot likes to stuff on things. This is our chart of the 2000. The red, thicker songs are songs that ever hit number 1 in the chart. The thinner black lines are songs that never hit number 1 over the course of it. And then we see with week, this is that compressed axis, because most songs enter the Billboard Top 100 and leave within the first 20 weeks. Kind of want to chart them over time. So this is a nice, pretty plot. It's cool. Lets us see that, okay, the songs that hit number 1, maybe they have a slightly different trajectory than songs that never hit number 1. It also reveals an interesting data quality problem. See this huge chunk missing right here? There's some sort of censoring at work here. Songs that fell out of about the top 50 here are just missing from the data past week 20. I don't actually know why this is the case. I've never bothered to go look it up. But a plot like this reveals that maybe these data are shitty for songs that fell out of the top 50. But we're interested in top number 1 songs. Seem to be doing a pretty good there. Anyone have questions about this plot? How we did it? Anything not make any sense? It's kind of cool. Most of the songs follow sort of like this trajectory where they go here, but every once in a while you see something like this. This one comes out here, drops down, and then suddenly got really popular, and then jump back down again. It's kind of weird. That's the kind of one you go and investigate. Okay. So, another question you might have here is, say you want to know which songs spent the most time at number 1 on the chart. Take Billboard 2000, I select artist, track, and weeks at number 1 because I don't care about any variables except those. I say distinct artist, track, weeks at number 1 because I don't care about redundant data. So distinct is going to, if I have, say, 30 columns because one particular song was in that number 1 position 30 times or whatever, I only want 1 row for that. Distinct artist, track, weeks number 1. Then I arrange descending by weeks at 1. I got the first 7 songs. So we see this Destiny's Child song spent 11 weeks at number 1. Santana here at 10. My boy Enrique managed to make it up to 3 here. Not doing too bad. So, useful question we might want to answer based on our data we've assembled. Okay, now we're going to talk about dates and times. Okay, so we have the date those songs first charted, but we don't have the dates for any of the later weeks. And if you remember, all those weeks on that chart were not lined up in any logical way. Everybody was just starting at week 1, but everybody's week 1 is a totally different thing. Okay, we want to make this a little bit more logical. So what I'm going to do, I'm going to overwrite Billboard 2000 again with a modified version of it. I'm going to say Billboard 2000. We're going to mutate a new date variable. The date variable is going to be the date at that given week. So each row is a different week. We can calculate that pretty easily if we think about the fact that, well, every week should just be 7 days after the previous week. So what we can say here is date equals date.entered, which was the date that it entered the Billboard Top 100. Then any given week, whatever that week numeric is, I want to subtract 1 from it so that the week when it was in its week 1 should be the same as date entered. And then add 7 days to it for every additional week. So this Tupac song here, in week 2, it should be 7 days after the previous one, 7 more days, 7 more days, so on and so forth. Okay? This works because R recognizes with date objects that the unit is in days. If you take a date object and add the number 1 to it, it increments it by 1 day. And it counts the months appropriately. A month with 30 days, if you get to 30 and add 1 to it, it will increment to the next month correctly. It understands calendars and things. Trying to manually do calendar manipulations is horrible because you have to come up with special code that handles every single 30, 31, the 128 day differently. God forbid you've got leap years in there, that kind of stuff. Okay? Don't do it manually, use a package for it. Anyway. Okay. So, now we have something cool. We've converted our crappy kind of useless week number here into the actual dates we can use to plot these things. So we can actually see how the different songs at different times of the Billboard hit number 1, and logically in any given week, no 2 songs should be number 1 at the same time. Those things are mutually exclusive. Okay, so now I'm going to prepare to plot over calendar time instead of over weird week time. Okay, I'm going to generate a plot called plot by day. ggplot our Billboard 2000 data. Instead of week, now in X we have date. We're going to be running date along the bottom instead of meaningless week. Y is still ranked. Group is still tracked. Geomline is basically the same. Size 25, alpha 0.4. I've no longer sized them out separately for the different types. Scale X date. So this is a ggplot special function. Scale X date. This is saying, oh, X is a date time object. You can tell it what you want the breaks and scale of the time date object to be in. So in this case, I say, oh, I just want a tick for each month, and I want the labels to be the short month names. %B means 3-letter month shortened names like SEP for September, OCT for October. Don't worry about memorizing all these codes. Just figure out your favorite ones and remember to use them. Again, I reverse the scale, theme black and white. Now I'm going to add 2 additional things here. I'm adding 2 vertical lines. I'm adding a vertical line on the 1st of January and the 31st of December, so the beginning and the ending of the year. The reason for this is some songs were on the Billboard Top 100 that entered it before the year started, but they're still in the data if they entered earlier, as long as they were on it sometime during the year. And some songs stayed on the Billboard Top 100 past the year, but because they started during the year, they're still in the data. We'll see that in a second. Notice how to make these lines go where I want. I gave it time date objects. I said, I want this to be year 2000, January 1st, and I had to say, format it as %Y is 4-digit year, %M is 2-digit month, %D is 2-digit day. Okay? This is the new plot. The new plot has a red line on the 1st of January and on the 31st of December, and then this mess of spiderweb shit is every song's trajectory over actual calendar time. Okay? And you see, some songs began on the Billboard Top 100 here way back in just near the start of June in the previous year, 1999. It's still in the data because it was persistent and managed to make it all the way over here. Similarly, we have some songs that were on here and they charted all the way off. Eventually the data are cut off from the look of it, but these songs kind of shot up and go. Okay? And if you look really carefully, you'll see no 2 songs ever occupy the #1 spot at the same time. Kind of hard to tell, but trust me. So, pretty confident it worked. This is the thing I was talking about, the 3-letter abbreviations for all the months. %lowercase b does that. Okay, questions about that? I recommend looking at code like this kind of thing if you want to do something similar. Stealing it outright, fine with me. Okay, so, dates and times. Whew. Okay, to practice working with finer grain data, I pulled down here some Seattle Police Department response data for a single day from data.seattle.gov. I'm going to kind of breeze through it and not worry too much about it. These are interesting data because they have things like the latitude and the longitude of the call. I'm going to use these later in the term. Basically, it's just crimes that happened, actual crimes in Seattle. We're going to play with them based on their actual time, like the hour of the day. Okay, so take a quick glimpse at them. We have things here like the event clearance description. So for instance, theft car prowl. Theft car prowl means somebody broke into a parked car and stole things out of it. No intention to steal the car, they want to steal stuff inside of it. Shoplifting, things like that. You also see this trespassing, all that kind of stuff. We have exact locations, we have beats, we have blah, blah, blah. But what we have is at scene time when the cops arrived, which might be of interest to us. Okay, so, first thing. I get structure on SPD raw $event clearance date, and we see we have something that is a kind of a time date object. We have month/day/year, then we have hour, minute, second, and PM. Okay? What we want is we want this to be in a date time format. In R, it's normally what is called POSIX CT time. If you want to know way too much about how computers think about time, Google POSIX time and then go down the hole. POSIX time is measured in seconds since January 1st, 1970. All computers count from 1970. It's just the way they do it. Anyway, we're going to work with looper date. Lubridate, I don't know if it's built into the tidyverse. You may have to install it. Anyway, library of Lubridate. What I want to do is I want to convert this event clearance date and time into a single date time object. So I say, take SPD raw, mutate event clearance dates. I'm going to overwrite this original variable. This is a function in Lubridate, MDY underscore HMS. This means whatever data I'm giving this function is in month, day, year. So we see month, day, year, hour, minute, second, and then I want Lubridate to figure out the rest of it for me. I just say give it event clearance date and tell it we're in the America/Los Angeles time zone. I give it nothing else. I don't tell it these things are separated by slashes, these are separated by colons. I don't tell it there's a space here. I don't tell it that it's AM and PM over here instead of 24-hour time. Lubridate figures it out for you. It's like, okay, I know how to parse this crap. What pops out is a new POSIX object, POSIX CT, Unix time is really what it is. Format 2016-03-25, because R, like a logical thing, counts in descending size of objects, year, month, day, and then hour, minute, second, and it's in 24-hour time instead of being in 12-hour time. Lubridate took care of all of the hard work of processing and dating time for us. That is really cool. Used to be back in the day you had to manually tell it, okay, it's going to be the month, there's going to be a slash, there's going to be a day. Oh, and month is 2 digits, not 1 digit. This is 4-digit year, a space, blah, blah, blah. Tell it how to parse all that stuff. You'd have to manually add 12 to it if it encountered a PM. Anyway, don't do that anymore. There's a function like this, MDY-HMS, for every possible configuration of these numbers. Just use a different function. It automatically tells it how to parse it. Okay. So, an aside that I kind of hinted at a minute ago. Time data are really weird. So there's 2 primary formats for storing time data in R and also pretty much everywhere. They are POSIX CT and POSIX LT. POSIX CT is a numeric vector of seconds since January 1st, 1970. POSIX LT is a big list of vectors that contains lots of weird date-time information. You can store dates as either one, but POSIX CT is a little easier to work with. Lubridate has lots of functions for converting things into POSIX time and manipulating objects that are in POSIX time. If you want to do any kind of math with times and dates, I would say immediately just convert them to numeric values, work with them as normal numbers. But if you want to work with them as actual times and dates, keep them in POSIX time and do things with Lubridate. Okay, some useful functions. So let's say I want just the date of something. Remember event clearance date? Event clearance date was a date and a time. Often you only care about one of those things, the time or the date. If I say as.date and give it a time date variable, it will spit out just the date being a year, a month, and a day. Basically just cuts off the time information. You can extract things from dates and also from times, like the weekdays function. If I say weekdays on a date object, oh, well it says that that day was a Friday and that day was a Friday. It extracts the appropriate weekday. Now if you think about it, that's something that can't be done easily mathematically for most people, figuring out what is the actual day of the week, because it doesn't have a logical connection back to something numeric. It's because it's referring to a general calendar system. Okay? I might want to do something like do math with things. Like for instance, what if I'm not interested in a given hour, but I'm interested in what was an hour later? I could say, give me a particular date time object plus d hours 1. This says, I want to add 1 hour to this. We looked at the original time, which I don't have shown here. This just increased it by an hour. But see here, this was in 2016-3/25. Well, this actually had occurred at 11:58 p.m. If I add 1 hour to it, it goes to the next day. It actually knows to increment day by day. This is why you work with date-time objects. If you just added 1 to it, you'd suddenly end up in the hour of the day of that doesn't exist, right? 24 or something. Date-time objects, don't do normal math with them unless you know what you're doing. But if you do math with them, there's convenience functions.
So technically you can use it for explaining when it happened in different time zones.
Yeah, and you can also control time zones specifically. So if you have a bunch of different data that are in different time zones, you could adjust their time zones here and do appropriate like transformations based on time zones. Date-time objects store a lot of information in them, so it's really good to use them.
But if we type Tokyo, then does it change according to the time zone?
Yeah, it'll do things like it knows which ones have daylight savings and which ones don't have daylight savings. It will rotate the times appropriately. So if you could ask it something like, oh, well, this time is in the Tokyo one, what would happen if I converted it to Seattle? It would add the appropriate hours or shift the day as appropriately. It does all those kinds of time manipulations, just doesn't. So for people who are working with time and date way back on the flights homework, this would have made your life a lot easier, but I didn't want to get into it yet. Okay, so maybe we have a question like, what time of day were most incidents in our police data cleared? So I'm going to do something called, I'm going to create a new object, SPD times. It's my SPD data. I'm going to select the initial type group. Initial type group is the type of crime. Event clearance date, which was the time that it was cleared at. And then I'm just going to say, mutate, I'm going to create a new variable hour, which is just equal to whatever hour it was during that event clearance date. So it's taking all of that date time with the minutes, the seconds, all that kind of stuff. It's just converting it to a numeric hour of the day. So from 0 to 24, or 0 to 23. Okay, now I'm going to plot it. I'm going to say ggplot, take our times data, x is hour, so it's going to have the hour running across on the x-axis. No y variable, because I'm just doing a histogram. I say g on histogram, bin with 2, so it's going to be 2 hour-wide bins. Facet wrapped by initial type group. It's going to generate one plot for each type of crime seen in the data. And then doing some little tweaks with the theme. The strict.text.x is changing the text size on all the facets. Add a nice y label and x label. We get this. These are all of the different types of crimes seen in the police data and histograms of all of them hour by hour over time. So like at 0 here would be just after midnight and onward, down here at 20 being around 8 p.m. or yes, 8 p.m. Okay, at the top you'll see animal complaints, assaults, auto recoveries, casualties, disturbances, parking violations. And you'll see these things will follow certain flows of the day, which you kind of expect for some of them. Traffic-related calls are peaking right here, kind of late in the day, picking up people for Deweys and stuff like that. Suspicious circumstances occur mostly at night and in the early morning, there's a lot of stuff going on here. Parking violations peak here because the police don't have anything else to do in this period. It's low everywhere else. So they're getting parking violations. Okay, so we might want these data arranged in some other way. Perhaps we only care about the more common things, the ones that have lots of observations, so we want them first. To do that, we got to play with factor variables. Okay, so factors are a very common data type in R, and they're also really particular about what you do with them. So we need to know them a little bit better if we want to work with our data, especially if we want to plot data. Okay. So the order of factor levels controls the order of categories in things like tables, the axes on plots, the order of things in their legends, and the order of facets in ggplot. That's all based on the factor levels, something that is often kind of hidden if you don't know much about factors. Okay. Often, we want to make our plots come in some interpretable or aesthetically pleasing order. For instance, we want to order them by the highest to lowest values rather than just every plot of the states beginning with Alabama or something like that. Okay, so the lowest level of factor is treated as a reference for regression models, and all other levels will get their own coefficients. Very often we want a reference level to be something completely different than the alphabetical one. To do that, we got to mess with factor levels. Yeah, by default it's alphabetical. Normally don't want that, or often don't want that. Okay, so the 4cats package, built into the tidyverse again, is a package with functions that are 4 categorical variables. They're 4cats. This package replaces the functionality of a lot of base R factor functions with stuff that's more logical, more uniform in syntax, better error messages, that kind of thing, integrates with dplyr nicely. If you want to know more about it, This is a link to the manual for it. There's a lot of functions in there. Yeah, I don't think I mentioned it. Okay. Every function of use in the for cats package begins with the letters FCT. So if you want to autocomplete anything and you can't remember the exact function in for cats, type FCT and hit tab. It will list every function in the package. Cool and good, our packages do this now. Stringer, something we're going to deal with in week 7, I think. Every function in it begins with STR. I love it when packages do that, because every function is easy to get to. You don't have to memorize any of them. You just need to know how to open a list of them and then browse it. Okay, so one thing we might want to do is we might want to convert some character column to factor data. So I load up the library for cats. I look at this particular character column that I have in here. Things like theft, trespassing, crisis call. It's character data. Okay? I might want to modify the levels of this, so I'm going to convert it to a factor so I can do that. I say SPD times initial type group, so that is that particular variable. Parse factor that variable, and I say levels null. I'm letting it auto assign the levels to that particular factor. Now I look down at that variable. Now it's a factor with 30 levels. Theft, trespass, so on and so forth, and some particular levels to it. Now if I convert that variable to numeric, because it's a factor instead of character, it will pop out with the numeric levels for that variable. Okay, so I've made a factor. Now I'm going to do something with it. A common operation you might want to do is you might want to make it so your factors are ordered by the frequency they occur in the data, so that the first level is the most common level in the data. Something you very often want to do. This is how to do it. So, first I'm going to create an object called SPD volume, SPD vol. It's equal to the SPD times data I created before. I'm grouping by the initial type group. The initial type group, remember, is the type of crime. I'm going to summarize n events equals n. So this n events is going to be a number that is equal to the number of times that particular crime was seen in this data. I'm then going to arrange it descending events. Descending means that the very first row of the data is going to be whatever was the most common crime in the data set. The last row of the data was the least common crime in the data set. One row per crime. Okay, it's a summarized data. I've essentially created a frequency table of crimes and ordered it based on the frequency of crimes. Now, I'm going to create a new SPD times 2 object equal to our original SPD times, mutate initial type group, which is the factor variable we're interested in putting in the order of frequency, and I say parse factor, the same function I used before, initial type group the variable, but now I'm saying its levels are equal to SPD vol $ initial type group. So initial type group in this data set here has been ordered by the frequency of the observations. What this levels argument is doing is it's looking for the first name inside of that column and making that the first level of the factor. The last one will be the last level. So I've essentially converted a frequency table I created up here into an order of factor levels for the initial type group variable. Okay? Now I'm going to replot it. This is basically the exact same plotting code I did earlier. Now what we'll see is the most common crimes come first and the least common crimes come last. By reordering the factor in the data, we've reordered the plot. This is how ggplot works for ordering everything. You do not order it in the plot, you order it in the data and then plot the data. And the ordering of factors comes from the factor levels. If you want to know how to do this, look at this, study it, ask questions, play with it. Does that make sense? It's okay if it doesn't, too. I would just recommend poking at it. Okay, there's other ways to reorder things. So instead of going through all the trouble of doing that sorting, the generating, things like that, we can do kind of shortcut things. There's a function called FCT reorder, right? For cats, FCT reorder. Parse factor is the only one that doesn't begin with FCT. FCT reorder, what it does is you have some factor vector that you want to reorganize the levels of, some quantity you want to order it by, and some function you will apply to those quantities to go to order that factor. So this is useful for doing things like making legends that go from the highest to lowest value by the maximum of something, or making axis labels go from the lowest to highest value using the mean. FCT relevel if you give the argument ref, so FCT relevel is for manually adjusting like one level at a time or a couple levels. If you do FCT relevel reference equals some level of that factor, that will just make that level the first level and just push everything else past it. This is how you would set a reference level, say, to go in a regression model, where the only thing that matters is the reference category. Everything else is getting its own variable anyway. FCT relevel reference. Okay, so here's an example of reordering. I'm going to cut down the Billboard 2000 to just Jay-Z songs. So I say filter artist equals Jay-Z. Mutate track is a factor of the track names. Okay? So the first thing I'm going to do is I'm going to generate a Jay-Z plot here that has a bad legend. We'll see what that means in a minute. ggplot, X is weak, Y is rank. This is essentially the same plot as before, but cut down to just the Jay-Z songs. But I've now colored it and grouped it by the individual tracks. So each track is going to have its own different colored line so I can follow a single track. Well, it looks like this. So we could follow, for instance, if we're interested in where Big Pimpin' went, it went like this. If we wanted on I Just Wanna Love You, basically the same arc like that. The thing is, though, is we see the song Anything, well, alphabetically it's the first, but that song is sitting here. Big Pimpin' is here, that's actually in order. This song here is down here, it's kind of in order. This song is first, but it's last on the legend. Maybe what we want is we want our legend to actually mirror the popularity of the song, so it'll be in the same order as the lines. Right? It's not necessary, but for somebody like me, it would drive me insane to not do that, so we're going to go ahead and do it. Okay, we're going to take our Jay-Z data. Now I say mutate track equals FCT reorder. We're going to reorder the variable track by the variable rank using the minimum function. This is saying, okay, get the minimum of rank and then order this variable by the minimum of rank. Minimum of rank, of course, is going to be the best place on the Billboard Top 100 that song ever got. So a number one song is going to have minimum 1. We want to reorder that to factor level 1, right? So Jay-Z Good Legend is exactly the same plot. I had changed literally nothing. Now the tracks begin with the song that was most popular, the song that hit the highest minimum rank, and then go down here to the song that hit the lowest rank. So essentially, we've just reordered our legend by the top rank of all of these songs. It's a small tweak, but it makes the plot a little bit better. And we did it all in the data, not inside the ggplot call. Okay. Another thing you might want to do is when you subset data, especially data or subset factor data, you will sometimes end up with fewer levels remaining in your data than were in that factor to begin with, but R doesn't automatically get rid of those factor levels. Factors have a specific number of levels, and it's okay for them to have levels that don't exist in the data. There's sometimes reasons to do that. So, if you want to drop unused factor levels from variables or an entire data frame at the same time, there's a function drop levels. What I do here is, first I'm just showing this. The Jay-Z data, I filter down to just these two tracks. But if I get the levels of this track variable, remember, only these two songs are in it, that factor still has all the levels for the songs I filtered out, because the factor stores levels as metadata. I don't want the rest of those levels. If I send that into a regression model that doesn't know how to trim factor levels out, it's going to yell at me for having no observations for things that it wants to create variables of. Okay? All I have to do is say, take Jay-Z biggest, the data frame I created here, and I just pipe it straight into drop levels. Drop levels, if I don't give it a specific variable, will go down every factor variable in the entire data frame and remove all unused levels in every single one of those variables. Now I get levels of that track, and now it has just the two ones that are actually seen. If you run into weird problems that says like unknown or unobserved factor level, try drop levels and then see if it goes away. Okay. Okay, so your homework. The dark times are upon you. This is the first homework on cleaning actually legitimately messy data. So, what I have given you are vote tallies in King County from the 2016 general election. It is a 60 megabyte comma delimited file. I think it's comma delimited. you might want to check to make sure it's not tab separated, figure out the right function for that. Downloaded from King County. They can be found on the course website. These data have no documentation. Aside from what I provide to you in the template, you'll want to show your work on how you figured out and answered questions about the data, how you clean them up. There is an R Markdown template. I've provided a lot of information in it. Read carefully. Like right-click to download that RMD from the website, open it up in RStudio, fill in chunks, do things, document your stuff as you go. The homework is broken into 2 parts. For complete the first one for next week, the second part for the second week. I say here, it can be daunting. Do not wait until Monday to start. I am not kidding. This homework can be difficult. Some people just breeze through it. Most people take some time. Just don't start until Monday. I recommend reading the instructions closely. Do work with others. Please work with others. It will make your life easier. Use the mailing list and the Slack channel often. If you run into problems, do not sit there and beat your face against it. Ask for help. If you waste like hours on some particular thing, you're doing it wrong. Ask me questions. Part 1 is due not May 1st. God damn it. Part 1 is due next Tuesday, and then part 2 is due the week after that. Yeah, 2 parts. And let's say you don't quite finish in part 1 or it's really hard. When you start part 2, I will provide you a complete part 1 if you want to use that instead of your own one. Basically, a key will be posted. As you may have noticed if you went and looked on the website today, the key for the most recent homework was posted. All homework starting with last week's homework on will have full detailed keys posted. I didn't post keys for the previous ones because it's more like just do whatever the hell you want and then make it pretty. These ones now, there's expectations for what it should look like. Keys will be posted. Any questions?
Which data?
Hmm?
Which data?
The data are, so if I go up
Data
here.
is so much.
Yeah, so we go down to homework 1. These are the general election data. It says don't open them in a browser, but no one can tell me what to do, so I'm going to do it. Okay. Should load faster than that. You're only 60 megabytes. Okay. Well, is a file here, some raw text file. Just right-click and download it. Save it somewhere. Open it up. You have a template. So, for instance, this is the HTML version of it. I have pretty thorough instructions. So, actually read these things. Oh, sure, the date here is correct, October 25th. How to get the data in, how to load them, recommendations for functions to use to inspect data. I actually have subsections being like, process this variable and look at it here, all that kind of stuff. Look at these different quantities of interest. You know, it's got a table of contents. You can browse around and see everything you want to do. It looks huge here mainly because every time anyone in the past has run into a problem in this homework, I add more text to it to answer those problems. It looks huge. The actual code you write doesn't need to be huge. Okay. And then, of course, there's a part 2. You'll eventually end up plotting things like the Democratic support rates in all the precincts in Seattle for all the races, all that kind of thing. It's going to be kind of cool. And it's working with actual data, actual Seattle elections data. If you ever work with real elections data, it's going to be nice to know exactly how horrible it can be and how to work with it. Okay, any questions? More questions? Okay, get out of here. That's still loading. No, scam likely. I'm not answering you.